Hello, and welcome to the first video in this new series talking about nonlinear optics. These first two videos are going to be about SHG, or second harmonic generation, and really about all the orders of generation. I mean, once you understand how second harmonic generation work, you can kind of understand how the third and fourth and so on. It's all the same pattern. But this is going to be the first video in the two-part series about second harmonic generation. So if we're talking about SHG, or second harmonic generation, we have to understand, okay, well, what is it? What does it do? So if you had a SHG crystal, or again, a second harmonic generation crystal, and you inputted 800 nanometer light, you'd come out with 400 nanometer light. And the trend follows for higher wavelengths. If you had 1000 nanometer, you'd come out with 500 nanometer and so on. So you see the trend, you half the wavelength of light. Another way to say this is you double the frequency. So this is a case of frequency doubling. And so this is useful if you want to change around the frequency of your laser. And this is actually used in old green laser pointers. They couldn't find a laser diode that would emit in the green region, but they could find a laser diode that would emit in the infrared, which is half the frequency, or twice the wavelength. And so they do all their stuff in the infrared, and at the very end they'd have an SHG crystal, which would double the frequency, and out would come green light. So that's one use there. But the question is, if you wanted to figure out how would this work, what would you do? How would you approach this problem? Because figuring out how, I mean, you have a bunch of atoms here, so you can model it like that, and you have light coming in, but how could you figure out how 800 nanometer light could come in and 400 could come out? It's not an easy problem to tackle, and that's what I hope to answer in this video, is how does SHG work at a molecular level? How is it possible that a bunch of atoms can turn 800 nanometer light into twice the frequency? And it's a hard problem to tackle, but we're going to work our way up. We're going to go with basic cases and move on to this full problem. So first case we're going to work with is a free electron. So consider a free electron in space, no atoms, just in a vacuum, just a free electron. And so what would happen if we shot an electromagnetic field at it? I'm just representing the electric field here. What would happen? Well, we know the electron is charged, and this is an electric field. So as the electric field of the wave passes by, it's going to jiggle the electron. And we know when you accelerate a charge, you also generate an electric field. So the input electromagnetic field is coming by, it's jiggling the electron, and as the electron jiggles, it emits light as well, right? Because you're accelerating a charge. And so notice how the light that comes out is dictated by the electron's motion. That's going to be a key thing to mention here. And so this is the first case, right? So the light comes in, it jiggles the electron, and as the electron jiggles, it emits light, and the light that is emitted is dictated by the electron's motion. That's a key thing to mention. So what if we had this case? What if we inputted light that is so intense that, let's say, it's so intense that the electron can't respond to the field? Let's say that the field is so intense that the electron would have to accelerate faster than the speed of light to keep up with it, let's say. What would happen then? So it's not going to be linear anymore, right? Because the electron physically can't follow the wave. So what would it look like? Well, if you graph the electron's motion, so this is the first case where it was, low intensity light. If you could graph the electron position versus time, it would just look like a nice sinusoid, right? So what would happen if you had the really intense case? Well, it turns out it actually looks something like this, right? So if you have really, really intense light, so intense that the electron can't respond to it, or it'd have to accelerate faster than the speed of light in order to keep up, it would look something like this. Now, would it look exactly like this? Absolutely not, because I mean, if you follow this, the electron would have to move up and then stop for a while, and then come back down and stop. Obviously, it's not going to look like that, but it's going to look something similar to this. What does it similar look like? It looks similar to a square wave, kind of, right? And so it looks similar to a square wave, and this actually provides kind of a conundrum, because remember, the light that comes out is dictated by the electron's motion, right? Here, the case was easy. The electron's motion looks like this, so the light looks like this. Here, the electron's motion looks like this, so therefore the light that comes out should also look like this, right? But this provides a problem. We know that electromagnetic fields, individual units of electromagnetic fields can only be purely sinusoids, right? Purely sines or cosines. This is not that, right? This is a sum of sines and cosines. And so since the electric field that comes out must look like this, we have to figure out, well, what happens, right? So we have this case. If we have really intense light so the electron can't respond, the electron's motion looks like this. And so since individual electromagnetic waves can only be sinusoids, we're forced to do this. We're forced to say, if the electric field that comes out looks like this, then we must conclude that it is composed of a bunch of sinusoids that add up to make this electric field. What I'm saying right now is the Fourier transform. So you Fourier transform the electric field to get all of its components, right? Since we know they must be sinusoids, it must be this signal must be a sum of sinusoids, and to figure out what frequencies they are, we'd take a Fourier transform. As you can see, that these are the first four terms, and they add up to give this square wave. And so if we take the electron's motion for this case, and we do the Fourier transform, we get this. And I did it in terms of harmonics, right? So if you consider this frequency to be the first harmonic, then it'll be right here, right? So it's going to be a significant amount of first harmonic, right? Because it looks pretty close. It matches the first harmonic really, really well. But then you need a third, a fifth, and a seventh, and so on in order to add up to make this electric field. So that's sort of the theme, is that the electron responds to the input light in such a way that it introduces higher order terms because the electric field is no longer a nice sinusoid, right? So in this case, the electron couldn't respond to the electric field, and so it kind of introduced these higher order terms because of its position in time. It was nonlinear, right? And so why is it only the odd orders? That's a good question. You can just Google online, why does a square wave only have odd harmonics? I'm not going to talk about that here, but it's a function of a square wave. So look up why does a square wave have only odd order harmonics, and there's plenty of explanations online. But that's the explanation here. So if you have a free electron and you hit it with an intense enough electric field, it'll actually emit the odd harmonics and in decreasing intensity, right? Let's consider in the next case. So let's consider, instead of a free electron, what about an electron within a crystalline lattice? Let's say this lattice. And an important thing to mention about this lattice is that it is centrosymmetric. So jiggling an electron to the right is the same as jiggling it to the left. Jiggling it one way is the same as any other way, right? So it's centrosymmetric. So because it's centrosymmetric, that means that if you were to graph the potential energy of this, remember in the first case the potential energy was 0, but here the potential energy is going to be symmetric about the equilibrium point. Right, so because remember, jiggling one way is the same as jiggling any other way, so that means it's going to jiggling it this way is the same as jiggling this way, so the potential energy should also be the same, right? So now we have an electron within this potential energy, and the question is, okay, if we drive this with an electric field, what will happen? With an electromagnetic field, what will happen? Well, it looks like this. It looks the exact same. Not the exact same, but it looks extremely similar to the first case. It actually looks like a square wave as well. Now, remember, this is dependent on the potential energy curve, right? Because you're going to be driving the electron in this potential energy curve like Tony Hawk, right? And so if the potential energy curve was like this, or like very broad, it's going to change how the electron position in time looks. So it's not going to look exactly the same. I just took the same graph. But this is dependent on the potential energy curve, right? So not all materials will respond the same. It depends on how skinny or how broad the potential energy curve is. And so, but it does look the same in the sense that it introduces all the odd terms in the same way. And so how do we know this? I keep saying these, oh, the electron's motion look like this, right? It's not like we take a microscope and look at it or anything like that. It's that we know the harmonics that come off, and so we can do a reverse Fourier transform to infer what the electric field must be or what the electron's motion in time must be. So that's how we're coming up with these things. And so the electron's motion looks something like this. Again, is it exactly flat at the top? Does it exactly stop and then just come back down? No, but it looks something similar to this. But so again, we can take the Fourier transform and see that it's all the odd terms. So we've done two cases. The free case, where if you drive with an intense enough field, you get all the odd harmonics. And same thing if you have an electron within a centrosymmetric material. But now let's consider our last case is a non-centrosymmetric material. So for the sake of clarity, let's say that the black atom is negatively charged. Jiggling the electron towards that negatively charged atom is going to cost you much more potential energy than jiggling it down, let's say, into this big empty space. So the potential energy is non-centrosymmetric, is not harmonic anymore. So jiggling one way is not the same as jiggling the other way. So this is an example of that. So I just took this graph. I mean, this makes sense. Like, let's say jiggling left would be jiggling towards this negatively charged atom, so it costs you very high in potential energy, but jiggling away still costs you in potential energy, but not as much, right? So what would happen now? And this is my attempt at drawing an asymmetric potential energy. If you were to jiggle an electron within this, what would you get? Now, it turns out you actually get this. You get a sawtooth wave. Now, again, it's not going to be exactly this, because notice how in order for this to actually work, the electron would have to basically teleport. It'd have to go from one place to another in an infinitesimally small amount of time. So obviously it doesn't look exactly like this, but again, it looks similar. It has similar features to this sawtooth wave. And again, we know this from the harmonics that come off. So if the electron's position looks like this, and let's think about why this kind of makes sense, right? If the electron's at the top here and it comes down, it's going to kind of like fall down very, very quickly, right? Because it's being driven by the electromagnetic field. So that's going to be this jump part, and it's going to slowly come back down, and then that's kind of this part. Kind of makes sense, right? But the point is the electron's position in time looks like this, because remember, again, the light that's emitted is dictated by the electron's motion. That's a very important thing I want to really nail in there. So again, it's also dependent on the potential energy curve. So if depending on how these arms kind of look, this will change, right? So that means not all centrosymmetric materials will act the exact same. It's going to be dependent on the potential energy curve that it has. So again, if you can take the Fourier transform of it, you get all the harmonics this time. So not just the odd ones, you get all the harmonics. You get the wave that's at this frequency and twice this frequency, and then so on and so forth, in decreasing order. And so now, if you want to do second harmonic generation, now you should know exactly what kind of materials you should be looking for. You should be looking for non-centrosymmetric materials, because we know that the free case and the centrosymmetric case only does the odd harmonics. I summarize that here. So when you jiggle an electron, the light that gets emitted is dictated by the electron's motion, right? So if you have it you put it in an environment such that it jiggles a certain way, it'll happen to emit light that corresponds to that. So if you have the free electron case and you jiggle it hard enough, it'll emit the odd harmonics. If you have the electron in a centrosymmetric material, it'll emit also the odds. And then non-centrosymmetric materials are the ones that emit all the harmonics, right? And so in the next video, I'm going to talk about, okay, you have a non-centrosymmetric material and you input light, you get all the harmonics. How do we isolate just the second? And how do we make sure that we get high yields for just the second? That's what I'm going to talk about in video 2. But this was the first video. I hope you enjoyed. Feel free to watch the other videos. And again, if you want to share this, please feel free. And I'll see you in the next video. We're going to be talking about, okay, we emitted all the harmonics. How do we get just the second? What engineering problems are we going to be facing? But I appreciate you watching, and thank you.